Okay, let's start the lesson activities for section 6.5. We have a matrix A and a vector B. Check that AX equals B is an inconsistent system. That is, show that it has no solutions. So we're just going to put in 1, -1, 1, 2, 4, 2, augmented with the matrix B, 3, -1, 5. We row reduce, and you get 1, 0, 0, 0, 1, 0, augment with 0, 0, 1. And this last row, it says 0x1 plus 0x2 equals 1, which is impossible. So this is inconsistent. No solution. Okay, so what this section taught us to do is say when you have an inconsistent system, we can find, there's no solution, but we can find the closest thing possible to a solution. We can find an x1 and an x2 that when you do A times it, so we're looking for A times an x, so we want to find this that is as close as possible to B. Okay, so we want to find what x can get us as close as possible to B, and we have these things called the normal equations, and that's how we do it. So the normal equations are A transpose times A times x hat, which is what I'm looking for, is equal to A transpose times B. Okay, so A transpose, that is 1, 2, -1, 4, and 1, 2, times A, 1, -1, 1, 2, 4, 2, times x hat, which is x1, x2, has to equal A transpose 1, 2, -1, 4, 1, 2, times B, 3, -1, 5. Okay, so now I just have to do a little arithmetic and figure out the solution to this thing. Okay, A transpose times A, that's going to give me, let's just make sure I can multiply them. This is a 2 by 3 and a 3 by 2. So I can multiply them because the 3's match up, and the result is going to be a 2 by 2. Okay, so I do the first row times the first column, and I get 1 plus 1 plus 1, which is 3. Which is 3. Okay, and then first row times the second column, and I get 2 minus 4, which is -2, plus 2 is 0. And then second row, first column, 2 minus 4 is -2, plus 2 is 0. And then second row, second column, I get 4 plus 16 is 20, plus 4 is 24. Okay, times x1, x2 equals, okay, so 3 plus 1 plus 5 is 9. And then second row times the vector, and I get 6 minus 4 is 2, plus 10 is 12. Okay, and then I solve this, but just by row reducing. So I'm going to do 3, 0, 0, 24, augmented with 9, 12, row reduce. And this will reduce to 1, 0, 0, 1, augmented with 3.5. So that means that my x hat, which is as close as I can get to a solution, x1, x2, is 3.5. Okay, so now next part here, part C, which I used all of its space. Find A times x hat. Okay, so A is 1, -1, 1, and 2, 4, 2. And I want to multiply that times the x hat I just found, 3.5. Okay, so I'm going to get 3 plus 1. This is going to be 3 by 1. Okay, 3 plus 1 is 4. And -3 plus 2 is -1. And 3 plus 1 is 4. 4, -1, 4. Okay, so part D says write B is the sum of a vector in the column space of A and a vector orthogonal to call A. B. Okay, so B, that was, let's just go back up and look. B is 3, -1, 5. So I want to write B as B hat, which is a vector in the column space of A, plus a vector orthogonal to the column space of A. We'll call that Z, to relate it to the notation we used earlier. Okay, so I forgot already. B is 3, -1, 5. Okay, so B hat is a vector in the column space of A. So that would be, if you look at part C, when I multiplied A times x hat, that gives you a vector in the column space of A because it's a linear combination of the columns of A. You put a 3 on the 1, -1, 1, and a 0.5 on the 2, 4, 2, and you add them, and so that is in the column space. So this is 4, -1, 4, and this is in call A. And then we have to figure out what do you add to get 3, -1, 5. So this would be -1, 0, 1. And then this is orthogonal to call A. Okay, so this next part is just to help us convince ourselves that we have found at an x hat, that's the vector that makes A times x as close as possible to B. So we want to look at the distance from B to ax hat and show that it's the smallest thing you can multiply A by. I mean, that it's the thing that you multiply A by that gets you as close to B as possible. So compute B minus ax hat. Okay, so B was 3, -1, 5. So 3, -1, 5, minus A times x hat, which we already computed on the in a previous problem, is 4, -1, 4. And I want to take the length of this. So that's going to be the length of 3 minus 4 is -1, -1 plus 1 is 0, and 5 minus 4 is 1. Okay, so that's the length of Z. So that would be the square root of 1 plus 0 plus 1. I just squared each component, adding them together. So that's the square root of 2. All right, so now I'm supposed to choose any x in Rn, in this case R2, other than x hat, right? So x hat was 3.5, remember? So I can pick any other vector in R2. Let's just pick a real easy one, 0, 0. Okay. And I'm going to compute B minus ax hat, or B minus ax. Okay, so A times x, A was 1, -1, 1, and 2, 4, 2. And I have to multiply that times 0, 0, and I will get 0, 0, 0. Then I have to do b minus that and take the length. So b, 3, -1, 5, minus 0, 0, 0, and take the length. So that's going to be the square root of 9 plus 1 plus 25. That's the square root of 35, and that is bigger than the square root of 2. Okay. So yes, square root of 2 is smaller than square root of 35. And no matter what you chose for this, no matter your choice here, this inequality should hold, okay? Because x hat, 3.5, that is the best you can do. That's the x hat that gets a times it as close as possible to b. So the distance between the two is as small as possible. Okay, now we're supposed to check whether the columns of A are orthogonal. Okay, so the columns of A, I'm just going to rewrite A here. It's 1, -1, 1, and 2, 4, 2. Okay, so are the columns orthogonal? So I'm going to dot. So I have 1 times 2 plus -1 times 4 plus 1 times 2. That is 2 minus 4 plus 2 is 0. Okay, they are orthogonal. Okay. So that means we can confirm the results we found earlier, the x hat and the b hat, by another result. Okay, this method only works when the columns of A are orthogonal, but since they are, we're going to do a little extra work and confirm what we have found. Okay, so we are going to use the inner product to compute the projection of B onto the column space of A. So that means we're calculating B hat, which is going to be B dot U1 over U1 dot U1 times U1. And U1 would be the first column of A. And then B dot U2 over U2 dot U2 times U2. U2 is the second column of A. So B is 3, -1, 5. Dotted with U1, 1, -1, 1 over 1, -1, 1 dotted with 1, -1, 1 times 1, -1, 1. Okay, plus 3, -1, 5 dotted with U2, 2, 4, 2 over 2, 4, 2 dotted with 2, 4, 2 times 2, 4, 2. And I am going to skip some of this calculation and tell you that this comes out to 4, -1, 4. Okay, that is the B hat that I found earlier. That was A times X hat. Okay, so 4, -1, 4. By calculating the projection of B onto the column space of A. So now I can give an equation using numbers only, relating the projection of B onto the column space of A, the 4, -1, 4, and the X hat. Okay, so I can say I'm looking AX hat equals B, AX hat equals B hat. So A, 1, -1, 1, times 2, 4, 2 times X hat, which is X1, X2, equals B hat 4, -1, 4. Okay, we can solve this by row reducing. augment with 4, negative 1, 4. And we're going to row reduce, and we get 1, 0, 0, 0, 1, 0, and 3.5, 0. So this says x1 equals 3 and x2 equals 0.5. So there's my x hat. Okay, we're going to do another problem like the previous one. I have a matrix A, 1, 1, 1, 2, 2, 2, and B, 0, 1, 2. If I try to solve this system AX equals B, this row reduces to 1, 0, 0, 2, 0, 0, 0, 1, 0. And this second row says 0 equals 1, which is impossible, which tells me that this system is inconsistent. There is no solution. Okay, so what I'm going to find is the set of least squares solutions x hat to ax equals b using the normal equations. And remember, the normal equation was A transpose A times x hat equals A transpose B. So A transpose is 1, 2, 1, 2, 1, 2 times A. X hat would be x1, x2. And A transpose times B. All right, so I just have to do a little arithmetic and solve this. So to multiply A transpose times A, I'm going to do row times column. My result's going to be a 2 by 2. So I have 1 plus 1 plus 1 is 3. And 2 plus 2 plus 2 is 6. And 6. And then 4 plus 4 plus 4 is 12. And this is going to be a 2 by 1. So let's see, I've got 0 plus 1 plus 2 is 3. And 0 plus 2 plus 4 is 6. So then I'm going to row reduce. I have 3, 6, 6, 12, augmented with 3, 6. Row reduce, and I am going to get 1, 0, 2, 0, 1, 0. Okay, so this has a free variable, which means there are infinitely many solutions. So this says x1 plus 2x2 equals 1. Solve for the basic variable x1 equals 1 minus 2x2. Okay. So I want to pick 3 sample solutions x hat. Okay, so any x1, x2 that satisfies this equation. Okay, so I can pick the x2. Maybe I'll pick 1 for x2 and then calculate x1. So if x2 is a 1, I have 1 minus 2 is negative 1. Okay, and then another one, if I pick x2 to be 0, 1 minus 2 times 0 is 1. And one more, let's pick x2 to be negative 1. So 1 minus 2 times negative 1 is 1 plus 2 is 3. And then it says compute A times x hat for each of these. So A was 1, 1, 1, 2, 2, 2 times negative 1, 1. All right, so I have negative 1 plus 2 is 1. 1, 1. Okay, and then I'm going to do the same thing for 1, 0. 1, 1, 1, 2, 2, 2 times 1, 0. And I get 1 plus 2 times 0, so that's 1, 1, 1. And then for the third vector, 1, 1, 1, 2, 2, 2 times 3, negative 1. And I'm going to get 3 minus 2, which is 1, 1, and 1. So it's always the same. I'm always getting the same thing. That's because 1, 1, 1 is my b hat, right? So I'm multiplying a times x hat, and I'm getting as close as possible to b as I can. This is as close as you can get to b, but still be in the column space of a. So let's go back and remind ourselves what b was. B was 0, 1, 2, right? 0, 1, 2. So that means that my b hat, 1, 1, 1, that's as close as I can get by taking a linear combination of the columns of A. The closest I can get to 0, 1, 2 is 1, 1, 1. So now it says write B as the sum of a vector in call A. So B was 0, 1, 2. A vector in call A, that's my B hat, 1, 1, 1. And a vector orthogonal to that. So that would be negative 1, 0, 1. This is B hat. This is Z. This is in call A. This is perpendicular to call A. I can look here. 3, negative 1. Or that actually, I have multiple x hats. I have to pick an x hat that does not, an x that does not satisfy this equation. So maybe if you let x2, maybe 1, 1. 1, 1 wouldn't work. Okay, I'll do 1, 1. Okay, so by definition, a times x hat is the closest you can get to b. So I'm going to do b minus ax hat. So b was 0, 1, 2. A times x hat was 1, 1, 1. And I want to take the length of that. Negative 1, 0, 1. So I'm finding the length of z here. So that's the square root of 1 plus 0 plus 1, square root 2. Choose any x in R2 other than x hat. So remember, x hat was... So that is not in my solution set for x hat. And now I'm going to compute b minus ax. B minus a times 1, 1. Okay, so b is 0, 1, 2. A is 1, 1, 1, 2, 2, 2. X is 1, 1. And that's going to come out to a vector that I need to take the length of. Okay, so that's going to be 1 plus 2 is 3, 3, 3. So that's the length of negative 3, negative 2, negative 1. Which is the square root of 9 plus 4 plus 1, which is the square root of 14. Okay. And it is true that the square root of 2, which is b minus ax hat, is smaller than the square root of 14. Okay, finally, check whether the columns of A are orthogonal. So I need to dot 1, 1, 1 with 2, 2, 2, and I get 2 plus 2 plus 2 is 6, which is not 0. So we can't confirm our results using the other method. That only works when the columns of A are orthogonal, so I can't do this last bit. I'm just going to leave it blank.